Hey guys, in this video I'll be just mucking around with some tensor calculus and Einstein's field equations and Ricci flow. So basically what I'm doing a little investigation on is under what circumstances do the laws of physics act like the Ricci flow. So when can the Ricci flow be applied to a manifold, an Einstein manifold, to kind of which does basically the same thing as the laws of physics would. So I've got the Ricci flow up here. It's probably not the best implementation of it for Einstein manifolds, but I don't care. We've got the Einstein field equations, and for the purpose of this I'll be ignoring the cosmological constant, and K is just the factor in front of the stress energy momentum tensor, which I think I'll just convert to Planck units further on down. So that just goes to 1. So we plug in this Ricci flow equation into the Einstein field equations, and the conservation laws in general relativity are encoded by the covariant derivative of this stress energy momentum tensor being 0. So if both sides, if this side here has a covariant derivative, I think it's contracted with mu, that equals 0, then the laws of physics are preserved. All the laws of physics are there. Taking in the covariant derivative of both sides gives us this, and it's equal to 0. And it's distributive over addition, so we've got 1 on each of these. And also the covariant derivatives, this is the contravariant covariant derivative, which isn't actually called the contravariant derivative, but it doesn't really matter whether it or not it has upper or lower indices. It'll work all the same, I think, anyway. I'm not very adept at tensor calculus, so you'll have to correct me if I've done any mistakes during this video. Anyway, so the covariant derivative obeys the product rule, so we can expand it out a little further. We get this. This middle term here is going to be 0 because of the Levi-Civita connection. So that just disappears, and we get something like that. The covariant derivative on a scalar field, which this R, the scalar curvature, is, just goes to the normal partial derivative with an upper index, and of course it's contracted with the metric, so we lower the index down and we get that. So we have this equation. So if this equation is satisfied by the metric tensor and this scalar, basically if the space is, and the matter distribution in the space implies that this equation is true, then the Ricci flow is actually acting as if it has the laws of physics. So one example of where this equation is satisfied is when in Minkowski space. So we just set our metric tensor to this. The blank spaces are 0, and of course that implies that time derivative of the metric tensor is 0, and of course Minkowski space is Ricci flat. So we get both of these equal to 0, and of course this equation is satisfied. So the laws of physics are exactly the same as the Ricci flow when we're talking about Minkowski space, so there's no matter at all. This probably isn't a very interesting solution to this equation. I'm pretty sure there are more. If I find any more, I'll post them up there, but I just thought it was an interesting question and I'd like to share with you. Anyway, thanks for watching, guys. Remember, if I've made any mistakes, which I probably have, point them out. Bye.